In this video, we're going to be looking at a new formula for the area of a triangle. It's based on the old formula, area equals 1/2 base times height. But what if you don't know the height of the triangle? Is there still a way to find the area? Well, you need a different piece of information, but it turns out that yes, there is. Before we do that, though, there's a piece of information that I'm going to use in demonstrating that formula that I want you to be comfortable with before we get there. Take a look at this diagram here. I have a set of axes, x and y. I suppose I could label those. And I have an angle in the first quadrant. Now, if I drop a vertical, indicate a right angle, and label the sides A, B, and R, actually, let's go ahead and label them X, Y, and R. X, Y, and R. Then the sine of this angle is equal to Y over R, opposite over hypotenuse. Now let's take a look at another angle in quadrant 2. I'll use a different color for this one, actually. Okay. And we're going to call this one, actually, let's call it phi. And the thing I want you to know about phi is that its measure is the same as angle theta. In other words, from here up to here is theta, and from here back to here is phi, and they're the same numerical value. Because they're the same numerical value, when I take phi's opposite and hypotenuse, the opposite will be y, it's above the x-axis. The adjacent would be the same numerical value as x, but in a negative, because I'm on the negative x-axis. And its hypotenuse would be r. But its sine, which does not use the adjacent side, is y over r. I hope that makes sense to you. Think about this angle here. Let me draw in for you. I'll use a thicker pen. This angle here as being the angle whose measure we want. So we use the reference angle phi, but recalling from a previous section that all of our trig ratios are positive in the first quadrant and sine is positive in the second quadrant. If these angles, theta and the reference angle for this large angle, which I'm calling phi at the moment, if theta and phi have the same are the same size, then they're going to have the same sine, and they're both going to have the same sine. They're both going to be positive. Okay, they both have the same sign, S-I-N-E, because they both have the same sign, S-I-G-N. All right, that's really all I wanted you to know about this, but I'm going to leave some information up here. Apparently I can only move some pieces at a time here. So let's see, I don't know how much I'm going to be able to move of my diagram. Oh gosh, not much. I would do this off screen, but this goes over here. I've learned that if I do this off screen, then it doesn't stick. When I come back to the recording, none of these moves have remained. So I have to do them on screen. I apologize. It's a pain to have to watch. All right, that can go there. Nope, that goes there. That's my y height, and these are my, oh, I don't know. Those are my axis labels, I think. There we go. That goes there. That's my x-axis, and that's my y-axis. Okay, apologies. That took longer than I wanted, but at least it's where we can refer to it. Now I'm going to take a look. This is another case of my moves not having stuck. I want to take a look at a couple of different triangles. Notice in both cases, well, I have a really hard time drawing triangles that don't look like right triangles, but I want you to imagine that this is a larger than 90-degree angle. That's an obtuse angle. Okay, so this is not a right triangle. This is larger than 90 degrees. And the same thing is true down here. This angle is larger than 90 degrees. In this case, my theta is one of the less than 90-degree angles, one of the acute angles, but there's an obtuse angle in the triangle. In this case, the obtuse angle is my theta. So we're going to talk about this one first. And I'm going to start by reminding you of the formula for the area of a triangle if you know its base and its height. So in order to demonstrate what that means, let's go ahead and label the height here. And I'll just go ahead and do it down here as well on this other triangle while I'm at it. Notice that when I indicate the height, I'm introducing a right triangle or a right angle. So now in both cases, I have a right triangle here and a right triangle here. Now this one's a little awkward because the right triangle is not part of the triangle whose area I want, but we'll come back to that in just a minute. Up here, I have a right triangle, so I have a relationship between theta and the height, which is important, right? So I could say that the area was equal to 1/2 times the base times the height, but if I don't know the height, then I still need to find a different way to work out this formula. I can say that the sine of theta is equal to the height divided by the hypotenuse of this right triangle, which is this segment right here. Let's go ahead and call that A. So my sine of theta is h over A, height over the side A. Now, if I multiply both sides by A, I get A sine of theta equals h. And I can replace h here with A sine of theta. So I get area equals 1/2 B times A sine of theta. And if I tidy that up, I get 1/2 times A times B times the sine of theta. Now I have to answer the question, what is B? Well, B is still the base of the triangle, so it's the length of this side here. I'll go ahead and label that B. This side here is A. So what we have in this formula here is that if you know two sides of a triangle, it doesn't have to be a right triangle, and you know an angle in between those two sides, then you can take the sine of that angle, multiply it by the product of the two sides, and cut it in half, and you'll have the area of a triangle. It's based on this familiar geometrical formula, but if we don't know h, we now have a workaround, right? So the reason I've done this diagram down here is because I want to illustrate that you can still use the same formula and how we know we can get away with that. All right. So the first thing to notice, I think I'm actually going to redraw this triangle because I want this angle right here to be more obvious. I want more room to work in there. My new triangle will still meet the same criteria though. I'm going to have three angles, obviously, that add up to 180, but one of them will be over 90 degrees. And that, in this case, will be the angle I'm interested in. Here, I had a larger than 90-degree angle, but the angle I was interested in was one of the acute angles. Down here, what if that angle is the one I'm interested in, the larger than 90 degrees? So let me redraw this. Okay, that's a bit better. Now if I drop my horizontal, that introduces a right angle. I'm including the extended base here, but as a dotted line because that's not part of my triangle. So I want to find the area of this triangle, but the right triangle I have to work with this time is completely outside the triangle I'm trying to find the area for. I will note that the hypotenuse of the right triangle is one of the sides of the triangle that I'm interested in. So let's label the base B, and the hypotenuse I'm going to call A, and this time my height is way out here outside the triangle. Now, if I wanted to find the sine of this angle, I'd be out of luck, at least at this point in the course. There is a way to do that, but we don't know how to do it in a non-right triangle. I can find the sine of this angle, but I need to know what that angle is. Because these two angles make up a straight line, which is half a circle, we know that they add up to 180 degrees. That means this angle right here is 180 degrees minus theta. That's its size. That's the size of that angle. So no matter how big this angle is, this angle is going to be 180 degrees minus that one. Okay, so now I can take the sine of that angle. I'm going to say sine of that angle equals opposite over hypotenuse, h over a. So I get the h over a the same way I did up here. The sine of this angle was height over hypotenuse, opposite over hypotenuse. Here it's opposite over hypotenuse. I'm looking at this right triangle right here, opposite over hypotenuse. If I multiply both sides, I get a times the sine of that angle equals h. Now, what is that angle? Well, we said it was 180 minus theta. But now I'm going to go back up to this diagram over here. And I said that, remember that this angle here and this angle here were the same size? Well, this angle is theta, and this angle is phi, but it's also theta because it's the same size. So one way to think of this, the size of this angle is theta. One way to think of the size of this angle is 180 minus theta. 180 degrees minus the same size as this one. Notice, though, what we said about these two angles, theta and phi, which we now call theta and 180 minus theta, they had the same sign. So the sine of theta is the same as the sine of 180 minus theta. What that means is that for sine, I can't do this with cosine or tangent, but with sine, whenever I see sine of 180 minus theta, I can replace it with just theta. Now I have that the height of my triangle is a sine of theta. So once again, I can replace h with a sine of theta and tidy it up, and I get the same formula. It's because the sine is positive in both of these quadrants that these angles, if they're the same size, have the same sign. So this angle here, which is 180 minus theta, has the same sign, sine, as just theta in quadrant 1. Because of that, I can get away with this substitution, which lets me use the same formula for both of these cases. They're both triangles with an obtuse angle in them. Whether the angle you're using to take the sine is one of the acute angles or whether it's the obtuse angle in the triangle, you can use the same formula. The trick is that the angle has to be between the two known side lengths, right? If I know these two side lengths and the angle between them is a known measurement, this angle between A and B, these two known measurements, that's when I can use this formula. All right, let's do an example. All right, let's suppose we wanted to find the area of this triangle. Then we have from our formula over here, the area is equal to 1/2 times the lengths of two sides times the sine of the included angle. That's the angle between the lengths of those two known sides. So let's plug our values in. The area is equal to 1/2 times A times B times the sine of 30 degrees. I can do this a number of different ways. I think I'll multiply 1/2 by 10. That gives me 5 times 8. And then the sine of 30 is 1/2. You can take that from your table. And then because it's easier arithmetic, I'll do 8 times 1/2. I can do that because multiplication is commutative. 8 times 1/2 is 4. And my answer is 20. That's it. Now, 20 what? I don't have any units here except for the degrees, and it's certainly not 20 degrees. Area is measured in feet or centimeters or, well, square feet or square centimeters, right? And I haven't given you any units for the lengths of the sides here. So in that case, what I would say is that it's 20 square units. And sometimes I cheat. When I want to say square feet, I'll say feet squared. When I want to say square centimeters, I'll say centimeters squared. That's a pretty common use of that notation. So when I want to say square units, sometimes I'll say u squared. I know that's cheating, but like I said before, mathematicians are lazy. As long as we understand that units is a U stands for a generic unit that doesn't have we don't know what the unit is. So we're calling it square units by using this notation. All right, let's take a look at another one. If I want to find the area of this triangle, I need to take 1/2 times A times B times the sine of, in this case, 100 degrees. Now, in this case, my triangle, my angle, the labeled angle is the obtuse angle. It's larger than 90 degrees, but that's okay. I can still use the formula. However, there's a different problem with this question. These two side lengths are given, but the angle is not included. In order to use this formula, I need to have this side length. So I wanted to point that out. I can't do this problem as it's written, at least not yet. I can, but not until later in the quarter. For now, though, I'm going to tell you what that other side length is, okay? Just so that we can work through the rest of the problem. I set it up initially on purpose so that was missing, to point out that I need the angle to be in between two known side lengths. If I don't have this piece, then I can't use this formula. Now, though, I can. Now I have that the area is equal to 1/2 times 4 times 8 times the sine of 100 degrees. And again, my arithmetic here is fairly straightforward. 1/2 of 4 is 2. 2 times 8 is 16. So I have A equals 16 times the sine of 100 degrees, because I don't want to confuse it with radians. Now, all I know how to find the sine for is, as an exact value, is 30, 45, and 60, or 30, 45, and 60 less than 180. 100 degrees for that is from any kind of a table or anything. So the only way to do this piece is on a calculator. Now, I've checked that my calculator is in degree mode because I've been given an angle in degrees, and I get 0.9848 for the sine of 100 degrees. It's actually 0.984807753. My calculator can give me more accuracy than this. So in writing my final answer, I've recorded this to 4 decimal places, but I'm leaving the whole thing out to, looks like 9 decimal places. I'm leaving all of that in my calculator, and now I'm just going to hit times 16, because then it will take the entire value that it's got stored in its memory and multiply it by 16. So I get 15 point, and this is my final step, my final answer. So in this case, I am just going to record it to 4 decimal places, 7, 5, 6, 9. As a matter of interest, what happens if I multiply just these 4 digits by 16? I get 15.7568. So I know it's way out in the 10,000ths place, or is it the, let's see, tens, hundreds, yeah, the 10,000ths place, but I'm already off by 1/10,000th. How accurate does it need to be? It needs to be as accurate as possible. So why, when it actually saves you a step not to retype this number. Leave the number that the calculator found for you, which is much more accurate than this. Leave that on the screen and just type times 16. It will automatically go and grab the most accurate version of this number that it has and multiply that by 16, giving you a much more accurate final answer. This is my answer for the area of that triangle, although I should say that it's approximately. In fact, the same is true here. This is where I started using a decimal. Okay, so I fill in my highlighter bubble there. So there's my final answer. 15.7569 is the approximate area of this triangle in square units.